Hey guys, welcome back to Genius Learning. Today I want to show a very common Physics 1 problem of how we deal with things sliding down a ramp. Okay, so the first thing we want to do is to draw our coordinate system, and also we need to understand how to break up this sliding object into components for a free body diagram. So we need to understand how to break up the gravity vector into components. Okay, so let's take a look. So first of all, I want to say for this problem, up is going to be my y, right? And that means this is perpendicular. It's perpendicular to this plane right here. Okay, that's my y. And then I want to say that going up the plane here is going to be the positive x hat, and where sliding down the plane this way is going to be negative x hat. Okay, and you can label that whatever you want, and usually you choose that based on the conditions of your problem. So this is a general understanding, so I'm going to label going up positive. So the second thing we want to do is now draw our gravity vector and break it up into components. And so for any object, right, this here, this line represents the ground. And so gravity always points downward towards the ground. And that vector is mg, right, the mass of the object times gravity. And then what we want to do is draw a line perpendicular to the object. That's going to be our normal force, right? That's the force that the ramp is pushing up onto the mass, and then the mass is also pushing down on the ramp, and so we're going to extend that line backwards now, like this. Okay, and we're going to stop there for a second. So these are perfectly straight lines right here. One is the normal, the plane is pushing up onto the box, and the one going downward is the box pushing down onto the plane. Okay, so these are the same line. Okay, first let's stop right there and let's look at what we have here. Inside here we have a 90-degree angle, okay, and we have a small triangle right here. And so this angle right here is going to be the same one as this top one here, because if you notice the 90-degree angle, the longer side has the theta, whereas the smaller side doesn't. And so if I'm looking at this 90-degree, the longer side has the theta and the shorter side does not. Okay, so with this small triangle here, I'm gonna do adjacent over hypotenuse. And so that way it's gonna be mg cosine theta coming downward, opposite to the normal force. Okay? Now, I want to extend a line or a vector from here, and I want to make it parallel to this plane right here. So this, I want to make parallel to this green line here. Okay? So this is parallel to this, and I did that because now here's another 90-degree angle and another triangle that we should take a look at right in here, all the way to the bottom this time. Okay, so now we're looking at this triangle here, and again the 90-degree, and this is the longer side here. So we have the 90-degree, and this is the longer side here, which has the theta. So the longer side has the theta, and the shorter side does not have the theta. Okay, so in this green triangle now, we're going to do opposite over hypotenuse, which still remains mg vector. And so this vector here, mg sine theta, we can also move this vector up here, and now this vector is mg sine theta. Okay, so we just moved this up here. Okay, perfect. So now that we have that, let's look at Newton's second law, F equals ma. Okay, so we have here the sum of the forces, the net forces equals ma. And what does that mean? Okay, so let's put a scenario onto this box. Okay, so I say that, or the problem says that somebody or something pushed this box up or had given it an initial force upward to slide up this ramp. Okay, so it was given a force, right? So it could be pushed up the ramp. And along this ramp is a very rough ramp, so it has friction. And friction is always going to oppose the motion, right? Friction wants to slow you down. And so it's always going to oppose the motion. If the box is going up, friction is going to go in the opposite direction. So we're going to draw this arrow here that represents friction with the lowercase f. Okay, and this green one is the gravity vector in the negative x direction. All right, so gravity is going down, but since this box is on a plane, it's pushing it to the left, which is downward, right? You can't go right through the plane. You have to like slide and then follow the plane's axis. Okay, so these are the forces playing into the box in the x and the negative x direction. And these two in the blue are the forces of the box in the y direction, right? So the box is not jumping up and down, right? And so these two forces, the normal and mg cosine, are equal. Okay, so making them equal means that this box is gonna slide right where it's at. It's not gonna go up or down, or it's just gonna slide straight across its axis. Okay, so knowing that, so we need the net forces, right? Because these things need to balance out, and we need to see what it comes out to. So we need the force net in the x direction first. Okay, so what are the forces in the x direction? We got a force going upward, and remember upward is positive because we labeled it that. This is the 0, so positive and a negative direction. We got a positive force going up, and then opposing that motion in the x are two things, are gonna be the force of gravity and the frictional force from this plane. So we got minus mg sine theta because it's going in the opposite directions to the force. And we also have minus friction because friction is also opposing the motion. And all of that equals ma in the x direction. So this is the acceleration in the x direction. All right, so what is friction equal to? All right, so let's write that down. So before moving forward to the force in the y, friction, I'll write it right here. Friction is equal to mu, which is the coefficient of friction, it's the actual number, and the normal force. Okay, so we'll take a look at what this means right now when we do the force in the y direction. So now the net force in the y direction, okay, since it's not moving up and down, then these two forces are equal to each other. Or we can say that the positive y direction, the negative y direction, right? And so we have the normal force minus, right, because it's positive, and then we have minus mg cosine theta is equal to 0, meaning they're balanced out, and this is not going to jump up and down. So if we pass the mg cosine to the other side, we got normal is equal to mg cosine theta. Okay, so we take this normal force, right, and we plug it into here. And now for friction, we're going to have mu, the coefficient of friction, times n, which we just found here, to be mg cosine theta. Okay, so we're going to plug that into there. And let's rewrite force in the x direction. All right, so we're gonna rewrite that here. And we have force minus mg sine theta minus, now the frictional force is this entire thing in here. So minus mu mg cosine theta, okay, and then equal to m and acceleration in the x direction. All right, since we're only dealing with one object, all the masses here are the same, and this could be a number, so we could have given it 10 newtons of force in this up direction. So that could be a number. We know gravity, the angle could have been given, the coefficient of friction could be given, or you can solve for acceleration by dividing by mass. So this equation here is going to be very useful for all types of constants and things that you're going to be asked. Okay, and so this is just one example of the box sliding upward. All right, in the next video, I want to show what happens when the box starts sliding downward and how can we calculate the same values with those conditions. All right.